A linear variable differential transformer, also known for its acronym Lvdt, is a linear position sensor that changes its output voltage depending on the position of a movable core. Its design is simple. The main structure is composed of a hollow tube of any material. It doesn't need to be ferromagnetic, but it helps the flux to move around more easily. A main coil is placed at the center of the tube. This coil is excited by an AC source, which creates a time-varying magnetic field. To the sides of the main coil, two secondary coils are placed and connected together, leaving a free terminal each to measure the sensor's output, which corresponds to the secondary coil's differential voltage. Finally, a ferromagnetic core is placed inside the tube.
This kind of sensor is based on Faraday's law of induction. The male coil induces a voltage and thus a current in the secondary coils, just like a transformer. When the tube is completely empty, the magnetic field reaches both secondary coils in the same fashion, therefore inducing the exact same voltage. The same happens when the ferromagnetic core is placed in the middle, right beneath the main coil. In these cases, the output voltage is zero.
When the core is moved to another position, the reluctance of the medium is reduced drastically because the air gap of the hollow tube is now replaced by a ferromagnetic material, therefore dragging the magnetic field towards the side, allowing more flux to flow through the coil and, of course, inducing more voltage than in the other coil. The more the core approaches to any given secondary coil, the more voltage that is induced in it and vice versa. Thanks to this, it is possible to know the exact position of the core, since the output voltage ratio is directly proportional to this. It is important to mention that since the primary coil is being excited by an AC source, the output will be an AC voltage. Therefore, it is necessary to rectify and apply a low-pass filter in order to process the signal.
To make the sensor, a PVC tube with a diameter of 2.5 centimeters and lamellar copper wire, insulating tape, and a plastic belt were used. The tube was separated into three sections of 6 centimeters each, where the coils will be later placed. 120 turns were given to each coil. Between each of them, a plastic belt was used to mark the boundaries. Finally, the coils were covered with isolating tape to fix them. To test the sensor, an iron drill bit was implemented as the core, and the AC power source was set to 5 volts peak-to-peak and a frequency of 1 kHz.
In this demonstration, the blue signal corresponds to the right secondary coil, whereas the yellow one corresponds to the left one. It is possible to observe that as the core moves along the sensor, these signals change according to its current position. As the core moves to the right, the blue signal's amplitude increases and the yellow signal decreases. The opposite happens when the core moves to the left. As it may be seen, when the core is placed just in the middle, both signals have the same amplitude but inversed, meaning the differential voltage is zero. As it was previously mentioned, both output signals should have been taken together and conditioned using a circuit like the one shown, but unfortunately every try to do so was unsuccessful. This probably happened because of the great amounts of noise within the system, as well as the extremely low output voltage of each signal. Also, since there were no switches available to turn the sensor on and off, a normally closed push button was used to take care of this matter. Although this is not practical, it serves well for demonstration purposes.
Finally, several tests were run to find the voltage-to-distance relation. First, the sensor's true center was found by finding the position where the output peak-to-peak voltage was the same for each signal. A value of 12.8 millivolts was measured. Then, the core was moved to the far end of the sensor to measure the peak-to-peak voltage of each signal at these points. It was found that any given secondary coil would give out 18.4 millivolts when the core reached its end, while the other one would have an induced voltage of 4.8 millivolts. Lastly, the core was removed to verify the induced voltage at both secondary coils was exactly 4.8 millivolts. Once the measurements were taken, knowing the distance to voltage relation is linear, it was calculated that 1 millivolt increase corresponds to a 1.33 centimeters shift.